Now, what is our solution to matrix equation AX equals B? Well, with matrices, and assuming you have the basic ideas of matrix multiplication, identities, and so forth, A inverse is the matrix which, when multiplied by A, gives you the identity matrix, and the identity matrix doesn't change anything that it's multiplied by. So that by applying A inverse to this side, we get A inverse A, which gives us A inverse A times the X vector, which gives us the identity times the X vector, which gives us the X vector. The X vector consists of X1, X2. Okay, so I've isolated this X vector on the left-hand side. On the right-hand side, well, if I multiply on the left by A inverse here, I got to do the same thing to the right-hand side, multiply on the left by A inverse, and I'm going to get A inverse B all the way down. So the X vector is A inverse times the B vector. So if you know the coordinates or the components of the B vector, you just apply A inverse to that and you get your solution X. Of course, we know that this equation doesn't have a solution, don't we? Because the matrix the augmented matrix reduces down to something that gives us no solution. So how's that going to come out? Well, we have a caveat. In order to multiply by A inverse, you've got to have an A inverse. And A inverse doesn't always exist. If it exists, we can find it, but it doesn't always exist. Okay, so we have to be careful about this. Now, we know that in order to get the inverse of the matrix, the A matrix, the 1, 2, 4, 8 matrix that defines this matrix equation here, that corresponds to this system, remember. So this is a matrix that corresponds to this system. If we can invert this matrix, we can solve the system. We're not going to be able to invert the matrix because we know we can't solve the system. Okay? So we write down the A matrix, we write down the identity matrix, and we proceed to reduce the system of matrices. Well, we don't get very far. You know, we got our 1, 2, 0, 1. And the obvious thing to do is subtract 4 times the first row from the second. So it's going to be and we're going to get 0, 0. And I don't know why I wrote 0, 1 here, because I'm not particularly, got enough sleep. I got no excuse. Okay. I think I wrote it down because that's what I saw here. Seems like my eye has more of a tendency lately to pick things up. Anyhow, well, we can do the second row minus 4 times the first, and you know that that's going to give us negative 4, 1. But right here, we're done. We ain't going to get the identity, because as soon as we got those 2 zeros, there's nothing more we can do. We can't undo them except by reversing course and getting something that's always going to be a multiple of the first row. There's never going to be a way to get a 0, 1 here, because any multiple of the first row that takes care of X is also going to take care of Y. Okay? So our conclusion then is we got no solution. Now I'm going to make a couple of comments about other topics. I'll comment right now, but I'll kind of write it down in the next video. If we take the determinant of this matrix, if you've been to determinants by this point, you see that the determinant of this matrix is 0. And you can also think for a little while and can come to the conclusion that any time the determinant of this matrix is 0, this is going to happen. Okay? in that case, we say that our matrix is non-singular. It's not invertible. If we say that our matrix is singular, it's not invertible. Okay? A non-singular matrix is one that you can invert, and inverting the matrix is the same as being able to reduce the matrix to the identity. Okay? If the determinant of the matrix is 0, you can't reduce it to the identity. And if you can't reduce it to the identity, the determinant is 0. So I'm going to write that and a couple of other things down. And then we'll make another connection with systems of this nature.